this module, we discuss a class of circuits classified as second-order circuits. These are circuits that contains resistive, inductive, and capacitive elements. So our objectives for this video will be to show the structure of the response of series and parallel RLC circuits, and to show how to solve for the complete response of these type of circuits. Let's say we have a series RLC circuit that is connected to a voltage source via a switch, and let's say that that switch closes at t equals 0. We want to know the response of the circuit, that is, we want to know what is I and the voltages across R, L, and C. So by Kirchhoff's voltage law, we can write this equation. So the total voltage across the elements is equal to the voltage of the source. We know that the V sub R, or the voltage across the resistance, is IR, V sub L is the IDT. So we can use those equivalent expression to rewrite the equation, and that will give us this one. Okay, so I've maintained the voltage across the capacitor as simply V sub C. Now we know that the current also passes through the capacitor, and that the relationship between the current and the voltage across the capacitor is given by this one. And I can also get the derivative of I with respect to time as C times the second derivative of the voltage across the capacitor. I can use this expression to substitute for I here, and this expression to substitute that in here, and that will give me this expression. Now simplifying this will give me a more simple expression that looks like this. Okay, now this is a second order differential equation, and the solution for the voltage across the capacitor, the complete solution, will contain two components called the transient component and the steady state component. So we can outright write the complete solution for V sub C as equals to its transient component plus its steady state component. To find the complete solution of the voltage across the capacitor with the differential equation given in equation 1, let's first solve for the steady state component of that solution. Now the steady state component can be found by letting the independent variable t in the complete solution to go to infinity. So that means that the value, that would be the value of the solution after a long time after closing the switch. Okay, so for a series RC here, if we let time approach infinity, or we wait for a very long time, that would result into a capacitor that is open. Okay, which will give us a current that is equals to 0. And when that happens, if we write KVL around this loop, that will give us this expression. So starting here, minus Bs times the voltage across the resistance, which is 0 times R, plus the voltage across the inductance, which is L, times the derivative of the current, which is 0 also, plus the voltage across the capacitor, which is the voltage after time infinity, and that should give us this expression. Okay, So solving for V sub c, that should give us the value for V sub c as V sub s. And therefore, that would give us the steady state component of V sub c as equals to V sub s. Now that we have the steady state component of V sub c, we can now proceed in finding the transient component of that voltage. But before we proceed there, we need to know something about the roots of the characteristic equation of the differential equation. So what is this? What are these roots? Let's assume for the moment that we let the source across the series RLC equals 0. So that is, we don't have a source. So that would give us a differential equation that is like this. Okay. Then from this, we can form an equation that looks like this. So this is known as the characteristic equation of this differential equation. And we can solve the values of S, which are called the roots of this characteristic equation. And that will give us two values, S sub 1 and S sub 2. Okay. So where alpha here is given by this, and omega naught is given by this one. So having found the roots, we can now state the transient component of V sub c. Now there are actually three types of transient components depending on the values of alpha and omega naught. The first case would be when alpha is greater than omega naught. Okay, so this is called an overdamped case, uh, where the roots S sub 1 and S sub 2 are both real and distinct. In this case, that will give us a transient component that is like this. So it is the sum of two exponential expressions, where A sub 1 and A sub 2 are constants and needs to be determined using the initial conditions of the circuit. If alpha is equals to omega naught, that will give us a condition called critically damped condition, and the transient component will look like this. Okay, and a third type is when alpha is less than omega naught. That means that will give us roots that are both complex, and that will give us a transient component that is a periodic function mixed with the exponential function, where omega d there, which is the angular velocity of the trigonometric functions cosine and sine, is given by this one. Hence, uh, the transient component will depend on the condition of the elements that comprise the series RLC. Now that we have the transient component, we can write the complete solution based on the case of the circuit. For the overdamped case, that will give us this complete solution. So here is the steady state component, and this is the transient component. For the critically damped case, we will have this expression, uh, and for the underdamped case, we have this complete solution. Now let's go to the step response of the parallel RLC circuit. So this is a circuit that looks like this. So it is a parallel combination of the elements R, L, and C. And this circuit, as shown here, is excited by a current source. Uh, so when there is no current source, the switch here is actually closed. So uh, if the switch is closed, that current here will simply flow in the short circuit path. Therefore, there's no current here. Okay, so the parallel combination does not receive any current. If the switch is open, the current here would be zero through the open path. So this is zero, and I sub s will flow directly to the parallel combination. So in this scenario, we are after with the solution of the current to the inductor. And so how do we form the differential equation? Take note that if this is IR here, and this is IC by KCL, on this node here, we have IR plus IL plus IC equals I sub S. Okay. Now we know IR to be equals to this is VR over R. Um, so this is still IL. So let's maintain that. And I sub C is C dVc dt plus I sub S. But V sub R is equal to V sub L. Okay, because they are in parallel, so this VR here is actually equal to VL here, which is also equals to V sub C. So therefore, we can rewrite this equation as V sub L over R plus IL plus C dVL over dt equals I sub S. But VL is equals to L di L dt. So therefore, VL here can be written as L over R DIL over dt plus IL plus CD uh, dt times L di dt, okay, equals I sub S. And if we simplify this differential equation, that will give us this dE here. Okay, so it's again a second order differential equation in the variable I sub L. And that will yield again a complete solution that contains a transient component and a steady state component. Okay, so after getting I sub L, we can therefore compute for V sub L, which is L dIL over dt, and V sub R is equals to V sub L, which is also equals to V sub C. And once we get these voltages, we can compute for I sub R because this is V sub R over R, and I sub C is C dVc over dt. Okay, so we can get all the responses, the voltages and the currents. We didn't explain on the series RLC how to get the voltages across the um, elements, but once we get there, the voltage V sub C, we can actually compute for the current as well. So The complete solution for the current to the inductance will also fall under three cases. So for the overdamped case, this will be the complete solution. For the critically damped case, this will be the solution. And for the underdamped case, this will be the solution, where the values for S1, S2, alpha, and omega, not including omega d, are given by these expressions. So let's have an example to showcase second order circuits. So here we have a circuit with a switch that is closed for a very long time already. And at t equals 0, that switch is open. So we are to solve for the voltage V across the capacitor at or for t greater than 0. Okay. Now, before we proceed with the solution, let me first explain what we mean by u of t. Okay, so this is called a unit step function. Okay, so ut is called a unit step function. Now, if we plot this function, that will function will look like this. Okay, so before t equals 0, the value of the function is 0, and at t equals 0, it jumps to a value of unity or 1, and it is 1 thereafter. Okay, so for ut really means that this is equals to 0 for t less than 0 and equals 4 for t greater or equals to 0. Okay, now let's proceed in finding the voltage V sub t for t greater than 0. So first, we need to know the scenario just before t equals 0. Okay, so this is the time when the switch opens. So just before the switch opens. So what is that scenario? So the scenario is that the switch is closed. So here is the switch here. It is closed. So therefore, this would be the circuit. And since we're talking about uh, before t equals 0, the current source here will be equals to 0. Okay, so for ut will be equals to 0 because 4 times 0 is equals to 0. So we can disconnect that source. Now the inductor, so this circuit here is at steady state. So meaning the inductor is like a short circuit and the capacitor is an open circuit. There will be current flowing through the inductor, and we call it I sub L of 0 with a symbol of a negative symbol on the upper right. And the voltage across the capacitor will be V sub C 0 with a negative symbol on the upper right also. So what are the values of V sub C and I sub L just before t equals 0? So that is the question there. Now take note that the circuit is at steady state. Okay, so before we go to t equals 0, let us first solve for this and this one. Okay, now uh, we can solve for I sub L just before t equals 0 using current divider, and that would be 3 times 10 ohms divided by 10 plus 5, no? 10 plus 5. And that will give us 2 amperes. And the direction of this current is towards the 5 ohms. We can also now compute for V sub C 0 minus, since this capacitor, which is an open circuit, is parallel to the 5 ohms. That would mean the voltage across the 5 ohms will also be the voltage of that capacitor. And since we already know the current here, the current there is also IL at 0 minus. So this would be 5 times 2, and that would be 10 volts. Okay. Now let's go to time t equals 0. So this is the time that the switch opens. Now, for a capacitor, the voltage cannot change abruptly. So therefore, the voltage at exactly t equals 0 must be equals to the voltage just before t equals 0, and that is 10 volts. Likewise, for the inductor, the current at exactly t equals 0 must be equals to the current just before t equals 0, because the current in the inductor cannot change abruptly. So therefore, that must be 2 amperes going to the 5 ohms, or going to the right. So now that we know the initial condition of the circuit, that is the initial conditions at t equals 0. So initial conditions means that what is the voltage of the capacitor and the current to the inductor. We can now proceed in finding the solution for V sub C at t greater or even equals to 0. This circuit, the part of the circuit on the left, is totally isolated on the right, so therefore we can forget about this part here and just concentrate in this part. But this part of the circuit is doesn't look like a series RLC or a parallel RLC. But what we can do to simplify the circuit is we can source transform this part here into a voltage source, and that should give us this circuit. Okay, where the voltage here is 5 times 4, 20 volts, and we simply copy the 5 ohms here from here. Okay, now the circuit looks like a series RLC, and therefore we can write the solution that we have already shown a while ago as uh, like this. So the solution would be the voltage across the capacitor will fall under 3 cases. And to know what case are we in, we need to know the values of alpha and omega naught. So our alpha here is R over 2L, and that is 5 over 2 times 1, and that should give us 2.5 per second. Okay, so the unit there is per second. For omega naught, This is equals to 1 over square root of LC, and that should give us 1 over square root of 1 times 4, which is zero point 0.5 rad per second. Okay. So as you can see, alpha is greater than omega naught, and this will tell us that we are in the overdamped case. Okay, overdamped case. And the solution for V sub C there is V sub S plus A1 e to the minus S1 plus S1T plus A2 e to the S2T. Okay, where S sub 1 is equals to negative alpha plus square root of alpha squared minus omega naught squared. So this will give us minus 2.5 plus the square root of 2.5 squared minus zero point 0.5 squared. That is equals to negative 0.0505, and S2, so this is S1, and S2 is equals to negative alpha minus square root of alpha squared minus omega naught squared, and that should give us a negative 4.95. Okay, and therefore the complete solution will be, so V sub S here is equals to 20, so that would be 20 plus A1 e to the minus 0.0505 plus A2 e to the minus 4.95, so this is T here, T. Okay, so that is the complete solution. And now we need to find the constants A1 and A sub 2. We can find these constants using the initial conditions of the circuit. Again, here is our solution for V sub C. So what remains is to determine A sub 1 and A sub 2. We also have our simplified circuit here. So this is the circuit as a result of opening the switch. So it is a series RLC circuit. Take note that the current is shown as directed away from the positive terminal of the source, and this is the same current that flows through the inductor and through the capacitor. We can use the initial condition of the capacitor, which states that at t equals 0, the voltage there is equals to 10 volts, so the one that we computed a while ago, and therefore we can write here 10 equals 20 plus a sub 1 e to the 0, because we have t equals 0, plus a sub 2 e to the 0, and that should give us a sub 1 plus a sub 2 equals negative 10. And we can consider this to be our equation 1. We can relate I to the capacitor with V sub C, and that is I equals C dV C dt. So this is 4 A1 minus 0.0 E. Okay, so simplifying this, we will get I equals negative 0.202 e to the minus so there is an A1 here, so minus 19.8. Okay, now I sub L is equals to I, so therefore this must be I sub L as well, right? Um, we can use the initial condition for the current to the inductor, and that is at t equals 0, we have I sub L equals negative 2 amperes. Okay, so why negative 2? Take note that the direction of the current to the inductor at t equals 0 is to the right, and that is 2 amperes. So therefore, we have to show that as a negative 2 here, because we're solving for I that is in the direction towards the left. So therefore, we can use this initial condition and write as negative 2 equals negative um, 0.202 A1 E to the 0 again, because t here is equals to 0, minus 19.8 A2 e to the 0, and that should give us uh, so we can cancel the minus signs. Okay, so we can make this plus, plus and plus, and that should give us 0.202 A1 plus 19.8 A2 equals uh, 2. And this could be our equation 2. Okay, so writing the equation 1 side by side, that will be a sub 1 plus a sub 2 equals negative 10. So this is equation 1 here. And we can solve these two equations, and that should give us a sub 1 equals as negative 10.205, and for a sub 2 that would be uh, positive 0.205. So this is 2 here. And finally, we could write our complete solution as 20 minus 10.205 e to the minus 0. Okay, so this is our uh, solution for the voltage across the capacitor. As a check, we can let t equals 0, and that should give us v sub c equals to 20 minus 10.205 plus 0.205, and that should give us a 10 volt, which is the same as the initial condition of the voltage, which is 10 volts. Again, here is our complete solution for V sub C, the voltage across the capacitor. As you can see, if we let T approach infinity, that is, we let the circuit go steady state, the voltage across the capacitor will approach 20 volts, okay? Because these terms here will approach zero because of the presence of the exponential function. We can also compute for I, which is, we said, is C dVc dt. So this is 4 times the derivative of Vc. So we already have Vc. And that will give us this current. Again, if we also let t approach infinity, so we let the circuit go steady state, we will get a current that will approach 0 amperes. I have prepared here a simulation for us to be able to better appreciate uh, how the voltage across the capacitor and the current through the inductor varies with time as we open and close the switches uh, that we have in the example. So right now I installed a voltmeter across the capacitor, and this will read the voltage across the capacitor. Also, I included an ammeter to the inductor that measures the current going in the leftward direction. Okay. So right now the 4 ampere source is isolated, and the 3 amperes here is the one that is connected to the circuit. So let me run the simulation. Okay. As you can see, the circuit is in steady state, and the voltage across the capacitor is 10 volts, and the current through the inductor is negative 2 amperes. Okay. So the same values that we got in the example that we have. Um, so I'm going to connect the 4 ampere source by clicking on switch S2. That will also open the switch S4. Okay. By the way, we can also view the graph of the voltage and the current. So right now the green line represents the voltage across the capacitor, and the dotted blue line represents the current through the inductor. Okay, so right now the inductor current is negative 2, and the capacitor voltage is 10 volts. Okay, I'm going to click the switch S2 now. Okay, so that uh, connects the 4 ampere source. At the same time, this switch is actually open. So as you can see, what happened to the current is that to the current to the inductor is that it went to a maximum value around 1.9 amperes, and then it starts to go down while the voltage across the capacitor is slowly rising. Okay, take note, we have computed the current to the inductor, the steady state current, to approach zero. So therefore, this curve here should go to zeros amperes. So the scale for the current is on the right, while the scale for the voltage is on the left. So this curve, colored blue, represented where the current to the inductor will actually approach zero, while the voltage will approach 20 volts. Okay, it is the change is a bit slow because the capacitor has a very high capacitance. So 4 farad is a very high capacitance. So this voltage, so it's now around near 15 volts, while the current is now at approaching 1 microamperes now. Okay, so this will go to zero while the green line will go to 20 volts. Okay, so we can also see it here. So the voltage in the capacitor, it's now 16.9 volts, while the current to the inductor is 6, it's decreasing, and it's now around 500 milliamperes. So as you can see, the voltage across the capacitor has reached 20, and that will stay at that level because that is the steady state voltage. And the current to the inductor will become zero, and that will be the steady state value of the current. So let's have our second example. Here we have a circuit where the switch is in parallel with a 10 ohm resistance. Um, the switch has been in the open position for a long time already. So the circuit is in steady state while the switch is open. We are required to find the voltage V naught across the capacitor. So again, we analyze the circuit before the switch is closed, the moment the switch is closed, and then uh, after that, what will be the complete solution for the voltage across the capacitor. So the before just before t equals zero, our circuit looks like this. So the switch is open, and the current to the inductor is constant because the inductor is acts like a short circuit. So the voltage across it is a zero, but there is a current, and it is a constant. The capacitor is like an open circuit, but there is a voltage, and that voltage is a constant as well. We can compute for the current to the inductor using current divider because the capacitor is open, making the 5 and the 10 ohms in parallel. So therefore, the current to the inductor is 3 times 5, that'll be 5 plus 10. Okay, and that will give us 1 ampere in the downward direction. Uh, we can also compute for the voltage V naught, the voltage across the capacitor. Uh, that will be zero because it is parallel to the inductor, which is right now um, acts like a short circuit. Then we go in analyzing the circuit at time exactly equals zero. So now the switch plays a role, and it shorts the 10 ohm resistance. Because of that, we can simplify the circuit, and that would look like that. So what is the current to the inductor? at t equals 0. Again, the current cannot change abruptly, so therefore it should be equals to the current just before t equals 0. So that is 1 amps, while the voltage V naught is also, and that should be 0 volts. So let us now go to time greater than 0 or even equals to 0. So since this is a parallel RLC, that means I sub L will have three cases. So we need to first compute for alpha, which is 1 over 2RC. So that will be 1, and that will give us 10 per second. For omega naught, it is still 1 over square root of LC, and that will be 1 over square root of 1 times 10. And that will also give us 10, okay, rods per second. So we have a situation where alpha equals omega naught. So therefore, um, the solution for I sub L will be a critically damped case. So therefore, um, I sub L will be equals to I sub S plus A1 plus A2 T e to the minus alpha T. I sub S is equals to 3 amps. So therefore, I sub L is 3 T. Okay. Um, okay. Now we need to find A1 and A2 using the initial conditions. We know that at t equals 0, IL is 1 ampere. So we substitute that here. So we have 1 equals 3 times plus A1 plus A2 times 0, because t is 0, e to the 0, because again this is 0. So therefore we have a sub 1 equals to negative 2. Okay, so that is a sub 1. Now for a sub 2, we need to use the initial condition of the voltage across the capacitor. That is at t equals 0, we have V naught equals 0. V naught is equals to VL because it is in the capacitor is parallel to the inductor, but VL is L di dt. So therefore we have 1 times the uh, derivative of I. So I is 3 plus A1. We already know A1, and that is negative 2 plus E2 T e to the minus 10 T. Okay, so let's compute for the derivative. So this is a constant, therefore uh, that will be so minus 2 plus a2t times the derivative of this, which is negative 10 e to the minus 10t, okay, plus this one times the derivative of this. So that would be, so the derivative of minus 2 plus a2t is a2. Okay, that's a2 times e to the minus 10t. So this becomes v naught. Applying this condition, so 0 was negative 10 times minus 2. So this is 0 e to the 0 plus a2 b to the 0. So that will give us a sub 2 equals negative 20. Okay, so therefore um, the final solution, or I sub L, this is not yet final because what we need is V naught. So I sub L now becomes 3 plus negative 2 minus 20 t e to the minus 10t. Here's the final solution for I sub L again. We can check the solution. So if we let t equals 0, we will get 3 uh, minus 2 plus 0 e to the 0, and that will be 1 ampere. Okay, so it's the same result that we got when we computed for the current to the inductor at t equals 0. So therefore, this must be correct. Okay. Now we now compute for V naught. We said this is equals to L dIL dt. So this is 1 times the derivative of IL, which is negative 2 plus 20t um, times negative 10 e to the minus 10t um, plus, okay, or minus 2. So the derivative of this, that is 20 times 10 or e to the minus 10t. Okay, so that will give us V naught equals so here we will have 20 minus 20 e to the minus 10t. So here Then so this is actually plus. Then plus um, 200 t e to the minus 10t, then minus 20 e to the minus 10t. Okay, so this term will cancel each other. So therefore, we'll have V naught equals 200t e to the minus 10t volts. Okay, so this is the final answer for V naught, and we can check it at t equals 0. We have V naught equals 0. And uh, we can check for the steady state value of this. Okay, so what would happen if t approaches infinity? What would happen to the voltage? Okay, so we can actually write this in this form. So 200t over e to the minus 10t. And if we let t approach infinity, both of the numerator and denominator will approach infinity. So we can apply L'Hopital's rule. So we so V naught there would be the limit as t approaches infinity of the derivative of the numerator, and that is 200, over the derivative of the denominator, which is 10 e to the minus 10t. Okay, so as t approaches infinity, uh, this will become very large, and sorry, this should be positive. Okay, and this should be positive as well. So as t approaches infinity, this becomes very large. So therefore, V naught there will become 0.